Hey guys, Mr. Betts here. I want to talk about something called Taylor polynomials, and we are going to use Taylor polynomials to approximate values of functions. And if you remember, we've done that before using something called linearization or linear approximation. So before we get into Taylor polynomials, I want to just do a little refresher on linearization. So if you remember, first of all, the slope of a tangent line is given by the derivative of a function at a point. And if a function is differentiable, so if it has a derivative and we can determine that slope, then that function is what's called locally linear. And essentially what that means is if we take a portion of that function and we zoom in on it, that's going to look like a line. So depending on how much we zoom in, it's going to look more or less like a line. But if you look at this section that I zoomed in on here, you can see that the red e to the x function and the blue function are almost identical within that window. So the idea of locally linear just means that a function is going to look like a line within some neighborhood around the point of tangency. So what we're going to do is with linearization, we're going to take into account the value of the function at the point. Okay, so that's just the point on the function. And then we're also going to take into account the derivative of the function, which gives us a direction or a slope. So for this particular function, y equals e to the x, we can approximate the e to the x function with the line y equals x plus 1. So again, if we're within a window or a neighborhood close to that point, then the points on this line are going to closely approximate the points on this curve. As we get further and further away from that point of tangency, that approximation is going to get less and less accurate. So what I want to do is talk about a way that we can make this approximation method better. So what we do take into account is the value of the function and the direction or the derivative, but what it doesn't take into account is how much the function's actually curving. So what we're going to do is we're going to try to take that into account also to improve our approximation. So the question is, how do we measure curvature? Well, a function that's curving, it's pretty ugly, a function that's curving is curving because the slope is changing. So if we look at the slopes of tangent lines, the slopes of those tangent lines are curving as we move along. We measure the change in slope by taking the derivative of the function that represents slope, which is the derivative of the function. So we take the derivative of the derivative and get the second derivative. So we essentially measure curvature using the second derivative. So taking that into account, what we're going to try to do is approximate a function using not only the value of the function and the slope of the tangent line, but we're also going to try to match up the concavity. Because remember, concavity is what we use the second derivative to measure. So let's look at how we can do that with this particular function. We want our approximating function to have the same value as the function. We want to have the same slope as the function, and we want to have the same curvature of the function. Notice that I said here that we're going to use a parabola. So a parabola is what I'm going to use because when we take the second derivative of a parabola, it's an x squared or second degree polynomial, we're going to end up with a constant. So instead of taking a straight line, which is a first degree polynomial, we're going to use a parabola, which is a second degree polynomial. So what I want to do is figure out what is the value of the function at 0, which is 0. Okay, that gives us our point. I want to figure out what the derivative is at 0. And the convenient thing about this function, and this is why I chose it for this particular example to introduce, is that the derivative is e to the x, and the second derivative is e to the x, and any derivative that we use is going to be e to the x. So f of 0 is 1, f prime of 0 is 1, and again, using these two, we got y minus 1 equals 1 times x minus 0, or y equals x plus 1. That was the equation of the tangent line. But now we're going to take into account the second derivative. And the second derivative is also 1. So I'm going to just write a general form of a parabola which is going to be y equals ax squared plus bx plus c. And this equation right here is what I'm going to use to approximate our e to the x function. So I just need to figure out what a, b, and c need to be so that it matches up with these here. I'm going to start with f of 0 equals 1. And in this case, I'm going to say y of 0 is equal to 1. And if we plug 0 in for x, we get a times 0 plus b times 0 plus c, which tells us that c has to equal 1. Then I'm going to take the derivative. So the derivative of this isn't very organized. Sorry about that. So we get 2ax plus b. So the derivative evaluated at 0 should also equal 1. And that's going to be putting 0 in for x. We're going to have 2 times a times 0 plus b. And so that's going to give us b is equal to 1 also. Now the second derivative is not going to be 1. So let me clear my... I didn't want to do that. So I'm going to take my first derivative and take the derivative, and we get 2a. So the second derivative evaluated at 0, which should be 1, is going to be 2a, and that's it. No x's in there, so nowhere to put a 0 in. And that's going to give us a equals 1/2. So what that means is the parabola, I'm going to clear this out and write out that parabola. The parabola y equals 1/2 x squared plus x plus 1 is going to be a close approximation for this function at the point x equals 0. And indeed, if we graph that parabola, you can see that the blue parabola is very close to the function in a bigger window. If you remember when we were using a tangent line approximation, I used a very small window and they looked really close. Now I can make my window quite a bit bigger, and the function and the approximation, remember the approximation is 1/2 x squared plus x plus 1, are going to be a lot closer to each other in a much larger neighborhood. So this idea here is just expanding linearization to include the curvature of a function in addition to the slope and value of the function. So let's look at a concrete example. We're going to use this parabola, which is y equals 1/2 x squared plus x plus 1, to approximate the value of e to the 0.1. So the whole idea is that the e to the x function is going to be approximately equal to that parabola in the neighborhood around x equals 0. Okay, and it's around x equals 0 because that was the point that I was using for our point of tangency. So in order to approximate this, e to the 0.1 is going to be approximately equal to 1/2 times 0.1 squared plus 0.1 plus 1. 0.1 squared is 0.01 or 1/100th, and 1/2 of that is going to be, so 0.01 divided by 2 is 0.005, plus 0.1 plus 1 gives us 1.105. Okay, so just taking out all the middle stuff, e to the 0.1 with our approximating parabola is about 1.105. So then the question is, did that really help us that much? How accurate is our answer? Well, if we plug e to the 0.1 into our calculator, we get 1.10517 and so on. And you'll notice that this is accurate to the first 3 numbers after the decimal place. So it's not until we get to the 10,000th place that our approximation is off. Now, this is different from the linear approximation. A linear approximation would give us a value of e to the 0.1 of about 1.1, and that's only accurate to the 100th place, which is not bad, but going all the way out to the 10,000th place is quite a bit better. So using a parabola at the point of tangency has the same value of the function, has the same value for its first derivative, has the same value for its second derivative. It improves on the linear approximation fairly significantly. So the question is, can we make it more accurate? So keep in mind the second derivative is what we use to measure how fast the first derivative is changing. Well, by including the second derivative, that allowed us to take into account the curvature. If we take another derivative, so if we take into account another derivative, that's going to take into account how much the second derivative is changing. And so we can keep adding levels of how much that higher order derivative is changing by taking another derivative, and we can keep improving on this. So what I want to do now is use what's called a third degree Taylor polynomial. So I'm going to get into in the next video specifically what that Taylor polynomial means. But the third degree Taylor polynomial for the e to the x function is, and I'm going to use this new notation here. Instead of y equals, I'm going to write t sub 3. That means third degree Taylor polynomial is 1/6 x cubed plus 1/2 x squared plus x plus 1. And I want you to notice that this part right here was the linear approximation. This part right here was the parabola approximation, so using the second degree or second derivative. And now including the third derivative, we're going to end up with that 1/6 x cubed. We can get this by using the same process that I used with the parabola. I don't want to go through that in the interest of time, but I do want to show how accurate this answer is going to be. So if we plug in 0.1, and that's going to be an approximation. Let's do this. E to the 0.1 is approximately equal to, so I'm going to plug in 0.1 here. It's 1/6 times 0.1 cubed plus 1/2 times 0.1 squared plus 0.1 plus 1. Now this is going to give us another approximation. I'm going to get that by just plugging it into my calculator, and I get 1.10516, and then the sixes start repeating. And if you remember, plugging e to the 0.1 into our calculator, we get 1.1051709, and so on. So I took this out a little bit further this time, and notice that now it's accurate all the way through the 10,000ths place, and even if we round the 100,000ths place, that's going to be the same also. So by adding one more degree to our approximation and including the third derivative in our approximation, now we've got a really, really accurate approximation for e to the 0.1. Now, I want to point out that e to the 0.1 is pretty close to 0, and 0 was our point of tangency. So let's look at what happens if we move further away from the point of tangency. So instead of e to the 0.1, let's approximate e to the first power. E to the first power is really just e. So that may be something that you are a little familiar with. E is, and I'm going to write it out fairly accurately so that we can check the accuracy of our approximation. So it's 2.7182818, and I think that's going to be enough to check our approximation. So our third degree Taylor polynomial approximating e to the x is 1/6 x cubed plus 1/2 x squared plus x plus 1. So when we plug in 1, it's just going to be 1/6 plus 1/2 plus 1 plus 1. So this is 2.5 here plus 1/6 is 2.6666, 2 2/3, repeating. So this is not real accurate. You can see that we're off already in the 10ths place. It's fairly close. It's only off by 1/10 ish. It's actually off by more like 5/100ths. So it's not as accurate though because we moved further away. if we go back to look at the graph, which I don't have handy here, but if we do go back to look at the graph, let's go back a few slides here. Keep in mind this is the parabola approximation, but you can see with the second degree approximation, as we get further away, that gap between them gets bigger and bigger. So no matter how many degrees of derivatives I use to approximate, if we get farther and farther away from that point of tangency, our approximation is going to get less and less accurate.